Hey, this is Joe, Gray Bench Electronics. Today I'm going to talk all about testing and selecting germanium transistors for guitar pedals. Alright, so a few topics to cover in this video. First off, we're going to talk about what a bipolar junction transistor is, or BJT transistor, which is going to make up the vast majority, if not entirety, of all the germanium transistors you are going to deal with as a pedal builder. We're also going to go over some of the considerations you need to have about germanium transistors as opposed to their much more abundant silicon counterparts. Then we're going to go over different ways that you can test the germanium transistors, different pieces of equipment. I have 3 different ways I'm going to show to test germanium transistors. And then we're going to go over why those transistor testers all give out different results and what that means for you as a pedal builder who wants to use germanium transistors. All right, so bipolar junction transistor, or BJT transistor. It's a very common type of transistor, maybe the most common type. You may also be familiar with other transistors like FETs or FETs, field effect transistors, MOSFETs, which are a metal oxide semiconductor field effect transistor. But BJTs are sort of the default setting for transistors. And the important feature I want to bring up with BJTs is, of course, what I mentioned earlier, which is that pretty much the entirety of all germanium transistors you're ever going to deal with are going to be BJTs. That's number one. I don't even know of any non-BJT germanium transistors. If they're out there, they're probably something very specialized. And the second thing that's important about bipolar junction transistors is that they are current controlled devices, or current mode devices. What does that mean? It means that we use current to control the flow of electricity through the transistor. So in the case of a bipolar junction transistor, you have 3 electrodes or 3 terminals. You have the base, you have the collector, and you have the emitter. Every bipolar junction is going to have at least those three connections as necessary in order to be a transistor. To be a current mode device or current mode transistor, that means we use a small amount of base current in order to control a much larger amount of current flowing technically from emitter to collector, but we use conventional flow, so it's collector to emitter. At least that's the operation in a common emitter amplifier, which is going to be the vast majority of your guitar pedals. Things change a little bit when you're talking outside of audio applications, right? We're using germanium transistors as amplifiers. Sometimes we're amplifying so hard, or we have the transistor biased in such a way that it clips heavily. That'll be a little bit different if you're trying to use germanium amplifiers for more linear applications or just audio amplification. But generally, when we're in guitar pedals, we're using germanium transistors because we specifically like the ways that they hit the rails or distort. So BJTs is a current control device, which means you use a small amount of base current, and that controls a larger flow of current through the transistor. That's the important part. It's different for different transistors. FETs are voltage controlled devices, so BJTs, current controlled or current mode devices. This moves right into our next topic, which is special considerations you need to have for germanium transistors as opposed to silicon transistors. And that all comes down to leakage. Leakage is basically a transistor being bad at its job. So a transistor, outside of the audio world, a transistor is most commonly used as a switch. And what you need a transistor to do in those applications is you either need it to turn all the way on, which we call saturation, or you need it to turn all the way off, which is shut off or cut off. Leakage is what happens when you can't turn the transistor completely off. It will leak a small amount of current from collector to emitter, even when there is no base current applied. That's what leakage is. For silicon transistors, leakage is usually in the very low nanoamps or even picoamps. For germanium transistors, it will be higher, usually in the microamps. Sometimes tens or hundreds of microamps. This leakage is not necessarily a bad thing. However, it is correlated with a device that's going to be noisier and overall less dependable. And so a good rule of thumb is a germanium transistor with leakage above 300 microamps is considered a reject, something you maybe shouldn't use for your design, especially not if you're going to sell the pedal to somebody. That being said, leakage isn't always bad, and sometimes you need leakage. The most famous example is one of the early fuzz pedals, the Maestro Fuzz Tone, actually requires a certain amount of leakage in order for the transistor stages to work at all. They are leakage biased. That is a factor that separates germanium transistors from silicon counterparts. Silicon transistors, generally speaking, we don't worry about the leakage because the leakage current is usually much smaller than the current that is flowing through the transistor during operation. For germaniums, though, that's not always the case. And we have to account for and test for the leakage in germanium transistors in order to know if they're going to be stable enough for our circuit, and at least have an idea about the noise of the transistor, and also considerations for the next topic, which is the gain of the transistor. So the gain of a germanium transistor is one of the most important features as to how it will operate in the circuit. Gain has many different names, and they all mean something slightly different. I'm not going to pretend to have a full grasp on all those different criteria for each one, but you'll often see gain listed as HFE, which is like letter H, letter F, letter E. You'll see that either capital H or little h, capital Fe, little fe. There's also beta, which is signified with the Greek letter B, which is beta. They all are generally colloquially used to specify for gain, and I will use them interchangeably. The ratio of the collector current to the base current is your HFE. So this can be expressed as an equation of the collector current equaling the beta times the base current. Or you can flip that around to say that the beta equals the collector current over the base current, which is a ratio. So collector current divided by base current, that is your HFE. That's assuming that you don't have any leakage. If you have leakage, then you have to subtract that out of the equation in order to know the true gain of the transistor. So any leakage current that's there, that is going to be there whether you are putting current into the base or not. That's why it's leakage. So in order to test for the real gain of a transistor, like I said, you have to eliminate that leakage current. So I'm not going to go too much more into that because we're going to look at it when we're testing the transistors for real. Also, most of this information is gained from an article written by R.G. Keen on picking transistor for fuzz phase. It is the quintessential text on this topic. These ideas are my own. So if you want to check out that article, it'll be linked in the description. I highly recommend you do because it is extremely pertinent, and really this video is almost just like putting that text into words. We're just going to go through the process and show you and show different ways you can do it. So enough of me talking. Let's look at some different ways that we can test germanium transistors for that gain and leakage spec, and we'll see how they differ and which ones are better than others. All right, so here are three of the most common ways to test germanium transistors for guitar pedals. There is a fourth, which is a digital multimeter, but you shouldn't use that method for the reasons R.G. Keen goes over in his article. Essentially, multimeters, they don't always make the test conditions for the transistor public, and they also do not account for leakage, mostly because people are testing silicons, which don't have much leakage. So multimeters pretty much out for testing germaniums, so we're left with these three. So over here we have something that looks really complicated, but it's actually really simple. This is the tester you can find in R.G. Keen's article. Again, if you want to check that out, there's a link in the description. It's just a couple resistors, transistor, and a battery. We'll look at the schematic or diagram in a second. Second piece of equipment we have here is the M tester, or what I call the M tester. You can find these on like Amazon or eBay. They're usually under 20 bucks, and they usually come with a little kit where you put together this sort of polycarbonate housing here. And this will test germanium transistors. Third option is a more professional unit. This is the DCA75 from Peak Electronic Design. They do make a cheaper version called the DCA55 that also tests germanium. So these are the three main ways that people test germanium. So I'm going to go over the pros and cons of each. All right, so first up, the R.G. Keen tester. Here is the diagram. You can find this in that article. So I have it here in a special breadboard. I think I've shown this before, but this is it's sort of a breadboard module thing from Pedal PCB that just makes doing the like ins and outs and power easier. But it's really simple. It's just two transistors that are carefully selected for resistance, a 9-volt battery that's as close to 9 volts as possible, germanium transistor, and a multimeter. I'm not going to go over exactly how this circuit works because R.G. Keen did it better than I could. So again, check out that article. But the simple gist is we're measuring the voltage drop across this collector resistor here. First off, we're going to have the 2.2 meg base resistor here not connected. And we're just going to measure the voltage drop, which is correlated to the current flowing through the transistor with no base current, which is leakage. And then we are going to connect this 2.2 meg resistor to the base, which is going to flow a small amount of base current, which will then increase, hopefully, the current through the transistor, and we'll measure the voltage drop again across this collector resistor. We'll then have two numbers. We'll have the no base current number, and we'll have the collector current, or excuse me, base current applied number, and we just subtract the former from the latter, and that gives us our true gain. The pros of this tester is it's probably the most accurate in terms of getting test results that are going to be as closely correlated to the way the transistor is used in the pedal. It also is a constant test, so as long as you have everything running and everything hooked up, you're constantly seeing updated measurements on your multimeter. So it's as constant as your multimeter is. The downside of this is it's a little more difficult to set up. You have just discrete parts, and you have to do the math yourself. It also takes longer to do the test because you want to let the transistor stabilize once you put it in the circuit and get it testing. But generally speaking, I would consider this test the most accurate or most applicable to us as guitar pedal builders who are building who are using germanium transistors for small signal stuff. Next up is the M tester here. So this tester, an immediate downside for this tester is it does not give you leakage. I'm not even certain that it accounts for leakage. It does that sort of subtraction that we went over for the RG Keen tester. The gain readings that I've seen seem to suggest that it does, but I can't be sure of that. I don't know the test conditions of this tester. I couldn't find those. The two measurements it gives you is it gives you the gain of the transistor, the HFE, and it gives you the forward voltage, I believe, of the base emitter junction. Remember, the BJT transistors are more or less just two diodes back to back, and so you can test for that forward voltage of the base emitter junction, which is essentially a germanium diode. So that's what this tester will give you. It'll give you the gain or a gain reading, and it'll give you the forward voltage of the base emitter junction. It is unclear what the test conditions are or whether this tester accurately accounts for leakage to give you real gain. But it's quick and easy and it's cheap. So those are pros and cons of that tester. Third tester is, of course, the DCA75 from Peak. This tester, again, is quick and easy. The tester is a bit expensive. It does allow you to do curve tracing, and you can use a computer to do those tracing operations. The tester here also does explicitly account for leakage. The main downside of the DCA75 is that it tests the transistors at a very high collector current of 5 milliamps. The reason it does this is a safety thing. It's trying to prevent excessive current from flowing through a transistor by slowly ramping up the base current until it sees 5 milliamps on the collector, and then it does the test at that point. Remember that gain is a ratio of the collector current to the base current. So this tester, it'll just apply a tiny amount to the base, see what the collector current is, and then slowly ramp the base current up until it sees that 5 milliamps. Like I said, it's a safety thing. If they just applied some known amount of base current, but the transistor had really high gain, then you could see way more current flowing the transistor than it could handle. So instead they do it the other way. They slowly ramp up the base current until they hit the 5 milliamps of the collector, and then that's where they do the tests. This tester does give you way more information than the M tester. You can scroll through all the different readouts. It'll give you gain, of course. It'll give you leakage. It'll give you the forward voltage of one of the junctions. So we'll see all that when we test the transistor. So these are the 3 germanium transistor testers. I'm going to pull some germanium transistors out of my stash. We'll throw them in the testers and see what they read out. They are going to be different readings for each one, and we'll talk about why that is and what that means for you as a builder. All right, so first on deck is the RG Keen tester here. Again, here's the diagram. Like I said before, this whole setup here is making it look more complicated than it is. It's just a couple resistors, a battery, germanium transistor, and the multimeter. The setup here, I have just a couple things to make my life easier. So this here, if you're curious, this is called a ZIF socket, and that's zero insertion force, a ZIF socket, and that just lets me put the transistor in and out without having to press the legs into the breadboard. I have the switch just sort of dangling off here. That's the switch that's shown in the diagram right there. The germanium transistor goes in the socket, and then I have the 2.2 meg resistor right there on the breadboard. That's the base resistor, and the 2.472K resistor is actually a little trim pot right there on the breadboard. It's actually a 10-turn, a multi-turn trim pot that allowed me to really dial in as close to 2.472 ohm resistance as possible. The article goes over why you want to get as close as possible, and it just makes your results more accurate when you're doing the mathematics. So we're going to turn on the multimeter to DC voltage. I'm going to pull a germanium transistor out of my stash. So I've got a little stash of, these are all used PNP germaniums over here. Just going to pull out any random transistor. Let's see. Just need whatever, doesn't matter. Here's an RCA 217 in the TO1 package, so probably 50s or 60s. You want to match up your legs. Generally speaking, for transistors, you'll find that they make sort of a little triangle with the legs. So you can see it's sort of a wep, 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 like that. And in this setup, if the collector is not marked, usually the collector will be marked with a red dot, and you can sort of see that there on the body. But in the setup like this, usually the emitter is the top right leg there, the base is the bottom middle, and the collector is the top left. And that's if you're looking at the legs like this. You may also notice that I'm using a tweezer to manipulate the germanium transistor, and that's because germaniums are very temperature sensitive. I'll demonstrate that here in the test, but essentially even the heat from your fingers can change the readings on the tester, and especially for the RG Keen tester here, where we're going to wait for the transistor to settle down into a stable reading. The more you test, or the more you touch the transistor, the longer you're going to have to wait for the transistor to settle back to room temperature. So I'm going to go ahead and pop this transistor into the tester here. All right, so I've got the transistor in the ZIF socket. I've got my multimeter on. It's hooked up to my probes, and we're just probing across, as the diagram shows here, just probing across that 2.472K resistor, or in my case, trim pot. I have, in this case, the breadboard is hooked up with its electronics to a DC power supply. So just going to flip the power on. And what's happening right now, because the switch is not closed, is we just have our multimeter reading the voltage drop across that collector resistor. And right now we're reading 2.65 milliamps. So there is 2.65 volts at the collector of the germanium transistor. And then, of course, ground is the other side. So what does that reading mean? Well, we can do some math to figure that out. If we're going to do it the right way, we're going to use Ohm's law, of course. Ohm's law is the most important equation of all of electronics. You should have it memorized. It's voltage equals the current times resistance. So we're measuring a voltage of 0.264 volts or 264 millivolts, and that's across a 2.472K resistance. So if we want current, we can flip around Ohm's law to tell us that current is equal to voltage divided by resistance. So we can take our voltage there, which is 0.264, and we can divide that by our resistance, which is 2472. And then we can see here, this is our current reading. And so first three is milli, and then after that is our micro. So we have 1068, so that's 107 microamps of leakage. If you want a little shorthand so you don't have to do that sort of figuring out of places, one thing you can do is take this number as a whole number, 263, and divide it by 2.472, and that'll show in microamps. The readout here is 106.3, so 106 milliamps. It's falling a little bit, which is a good thing. So 106 milliamps of leakage, that is a acceptable amount of leakage for me. Like I said, anything above 300 is where I wouldn't put in a pedal I would sell to anyone, unless it was a specific design that required a hefty amount of leakage. So now we have our current reading, our leakage current, with no base current applied. So I'm going to write that in on my little sheet here. So leakage was about 106 microamps, and this is a RCA 2N217, I think, right? So now we can do our HFE measurement. So we are going to flip the switch here. We're going to apply a little bit of current, about 4 microamps through that 2.2 meg that's hooked up to the 9-volt source. And that is going to cause the current to start conducting, or excuse me, the transistor to start conducting current, like so. So now that we've applied that base current, we can see the current through the transistor itself increased. So now we're dropping 1.13 volts across that collector resistance. So we're going to let this sit for about a minute. Once that's stabilized, what we'll do is we'll take that number and we're going to subtract the voltage that we read for the initial test. We don't want to subtract the leakage current we calculated. We want to subtract that initial voltage that was read across, and that will give us our true gain for the transistor. Gain doesn't have a unit of its own. You just write it as generally a whole number for the transistor. So let's just let this settle for a second. All right, so the transistor has settled out right now right around 1.21 volts across that collector resistance. Is going up very slowly, which is normal because as the transistor heats up, HFE does rise, and which means the collector current is going to rise even with the same amount of base current. For small signal, at least, that's true. Your HFE rises with temperature. So what we're going to do now is we're going to subtract the number we have here from the leakage test we did prior to this. Like, okay, we're at 1.216, and then we're going to subtract this measurement here, and that's 0.310. And that's our real gain right now. You just times that by 100, and that's the true gain. So about 90 HFE. So we're going to take that down here, 90. And like I said, there's no unit for HFE. Just take it as a generally whole number. So now let me show you what happens if you touch the transistor. So you will see, we'll go over here to the transistor in operation. So if I just put my hands on that, you're going to see that current start to shoot up. And that's because, like I said, the HFE rises with temperature. And so even though the same amount of base current is being applied, the transistor temperature is rising, which is causing the ratio of collector current, that sort of multiplication factor, to increase. And then we can let go, and eventually it'll start falling back down as it cools off. All right, let's test another transistor with the RG Keen tester here. This is a 2N1372. This is a Sylvania. It's got that cool little Sylvania insignia there. Another PNP germanium transistors. I should have mentioned, but this tester is specifically set up for PNP germaniums, which is going to be the majority of germaniums you're going to find. If you want to do NPN transistors, I think RG Keen goes over this, but you flip the battery and you flip your multimeter leads, and then you will be able to test NPNs. But we're going to pop this in the tester here. Again, not handling with my hands because we just saw what temperature does to germaniums. All right, so again, we're under the leakage test here with no base current applied. We're going to let this settle out here, and then we'll do our calculations. All right, so the transistor's settled pretty much on leakage here, so we have 0.262 volts across that collector resistance. So we can just take that 262 divided by 2.472, and that gives us 105, so about the same amount of leakage as that other transistor, which is just a coincidence. You'll have transistors all over the map in terms of leakage. So we'll write that in here. That's 106 microamps of leakage. Number here is also 264, so I'm actually going to write that down just so we don't have to come back to that. All right, so let's flip into the HFE or gain test mode. All right, so now we're getting current flowing through the transistor as we applied the base current. So again, we're going to let this settle down for a couple minutes and wait for a stable reading, and then we will do our math to get the real gain of the transistor. All right, so we're pretty much a stable reading now. We've got about 1.071 volts going across the transistor, or that collector resistor, with the base current applied. So we're just going to take that number, 1.071, and we're going to subtract the leakage current, which you can just flip back and see what that is. It's about 280 or so. I had 264 written down. So we'll cut in the middle. Let's call it 275. Oops, 1.071. Oh, minus 0.275. And then that gives us our HFE. Just times that by 100, and it's about 80 HFE there. So I'll write that down. 80 HFE for that. This is a Sylvania 2N1372. All right, so that is the RG Keen tester and how it works. Let's go ahead and move on to the M tester, and we'll look at the results from that. All right, so here's our M tester. Like I said, you can find these pretty cheap on like eBay or Amazon. Got the RCA 2N217 already loaded up. So all we do is hit the test button, and it will start testing. So pretty quick results here. tells us it's a PNP transistor. Symbol indicates it's a BJT transistor. It gives us our HFE of 93, and it gives a, looks like UF, but it's actually a VF, forward voltage of, I'm not even sure which junction, one of the two diode-esque junctions in the transistor. I usually like to do a second test just to make sure the results are consistent. So here we're getting 94 HFE and a forward voltage of 140 millivolts. Don't really care about the forward voltage, but the HFE we will take. And as you can see, it doesn't give us our leakage. So M tester for the 2N217, we're going to put down 94 HFE. Let's throw the Sylvania in there. One nice thing about this tester is you don't have to worry about the orientation of the leads like you did with the RG Keen, where it had to be in the specific sockets for the ZIF socket. You can just plop them in any which way, as long as they are in the three separate little sockets on the side here. The second bank here is all to 1. So it's like 1, 2, 3, and then these are all 1. So as long as you don't double up 1 and 1 on the side, you should be good. Here is the Sylvania transistor. Let's test that. All right, again, PNP gives us the BJT symbol, and we have an HFE of 77, forward voltage 162 millivolts. Let's do another test. All right, a little bit higher HFE, which is normal, 78. So we can write that down for our M tester here. 78 HFE for the 1372, and again, no leakage shown. Let's move on to the DCA 75. All right, here is the Peak Atlas DCA 75. So this doesn't use a ZIF socket like the other two testers did. They just use these little spring hooks. So we just hook one of these each to the 3 leads of the transistor. And just like the M tester, you don't have to do red or green or blue to any specific lead on the transistor. You can just hook them up any which way. And we can start a test here. So this is the RCA 2N217. So immediately it tells us it's a PNP Germanium BJT. It gives us the pinout. So it tells us which leads are connected to which. So red is connected to the collector, green is the emitter, and green is the base, and blue is the emitter. Now it shows us an HFE of 120, which is higher than our previous readings. So before we had 90 for the RG Keen tester, 94 for the M tester, and now 120 on the DCA 75 for HFE. And we can scroll down here, we see a bunch of stuff. It tells us that's HFE at collector current of 5.02 milliamps. So like I said, this is testing at a higher current, which is why we're getting a higher HFE. The HFE, like I said, it rises with temperature. It also rises at small signals with the finite collector current. So your HFE at 5 milliamps can be 120 for this transistor, but at 1 milliamp it might be 100 or 90. That is one of the differences between these testers that we'll go over. The forward voltage of the base emitter junction is 0.3 volts at 5 milliamps, at a base current of 5 milliamps. That's what that test shows. Voltage from collector emitter saturation voltage is 0.035 volts, and that's at the 5 milliamps of current. And at base current 1 milliamp. So it gives you a bunch of stuff here. And here's the leakage, 85 microamps. So that's 0.085 milliamps or 85 microamps. So we will write that down here, 85 microamps. So there's our results for the 2N217. Let's throw in the Sylvania. Takes a little bit longer than the M tester, but it gives you way more information. So again, PNP Germanium gives the pinout HFE 106 and tells you 5.18 milliamps, and gives you all the same information here. Going down the leakage, 70 microamps leakage. Let's just hit one more test just to be sure. Should have done that for the 2N217, but that's all right. HFE 107 and leakage of 72 microamps. So we'll write that down. HFE 107, 72 microamps. Okay, so there are the results for all three of for 2 different transistors and all 3 of our testers. So, as demonstrated by those 3 different test methods, you can get different results for the same transistors under the same environmental conditions, so like temperature and whatnot. So what does this mean? We got 90 HFE, we got fairly resistant HFE readings from the RG Keen tester and from the M tester, but we have significant higher HFE from the DCA 75. What does that mean? Is the DCA 75 wrong, or the RG Keen or the M tester, are they wrong? Well, the answer is that none of them are wrong. They're all correct readings based on the test conditions of the tester you used. So the DCA 75 is an accurate tester, and the HFE of that transistor was 120 HFE at 5 milliamps. RG Keen tester tests at much lower collector voltages. M tester, we would assume, also tests at much lower collector voltages, collector currents. So it's not that any of these readings are incorrect. It's just that you have to have the frame of reference. You have to know what the test conditions were, and you have to know how that applies to your circuit. I like the RG Keen tester in terms of accuracy because the currents that are being used in the RG Keen tester are similar to what you would find in a guitar pedal. 4 microamps of base current, yeah, that's in the ballpark. The DCA 75, 5 milliamps of collector current, that's a lot. So I think standardizing on the RG Keen tester, not only because it's an accessible circuit that RG Keen graciously made available for everyone, but also because it's closest to pedals, is a good thing to standardize on. So when we talk about HFE, I think we should talk about HFE readings from the RG Keen tester, at least for guitar pedals. And when we discuss, on the DIY forums and stuff, I think the RG Keen tester is the correct choice for the standard germanium test. You can use the DCA 75 or even the M tester for the speed and convenience, with the caveat that the readings you were getting are higher, and you will have to compensate that when you talk to other people about what HFEs you're using for certain pedals. Really, that's all it comes down to, is communicating those things between different people. If I say, well, one example is, for fuzz faces, we talk about 80 HFE for Q1, 120 HFE for Q2, where that allegedly came from Mike Fuller at Full Tone for the 69 fuzz pedal. But do we know what the test conditions were for those readings when Mike Fuller wrote about that? I don't know for sure what he used. So we have to be able to talk to each other using the same terminology and knowing we're using the same test to be able to communicate. So if I say, I built a fuzz face and I really liked using 80 HFE for both transistors, it's important to know how I tested my transistors for HFE in order to communicate that to other people. Or you could likewise have a problem where someone says, I know you're supposed to use like 80 for Q1 and 120 for Q2, but I found that I really liked 120 for Q1 and 180 for Q2. And they could be saying the same thing. The person who's saying they want 120, 180 could just be testing at a much higher current, and their transistors are equivalent to someone else's 80 and 120. So that's the gist of this, is that these testers are all probably giving accurate readings, but you have to know your test conditions to be able to communicate with other people. Armed with this knowledge, hopefully you'll be able to look at the HFE recommendations for different fuzz pedals or general guitar pedals you want to use, and know how to test germaniums, what the gain and leakage means, and how to apply your readings to those recommendations. I should also mention that this test is only for gain and leakage, but you do have to do more testing of the transistors to really know if they're going to work. These tests can't tell you anything about like self-noise of the transistor. You could find the perfect set of super low leakage, ideal gains for a fuzz face, but you put it in the circuit and it's snapping and crackling and popping and hissing like crazy. That's totally possible, and this test can't tell you anything about that. The RG Keen maybe could, if you see that measurement's jumping all around, but certainly not these two that just sort of take a snapshot. Okay, so we just went over testing germanium transistors and showing the results of 3 different tests and why those results differ. We covered what BJT transistors are and how they are current mode devices, and how the gain of the transistor is dependent on that current mode, how it's the ratio of the collector current to the base current, and also how germanium transistors leak. They don't turn fully off, and we have to account for that leakage. The last thing I want to leave you with is that while it is awesome that we can test and catalog the HFE and gain for our germanium transistors, this should not be the be-all and end-all. Don't get bogged down in these numbers. What really matters is taking those transistors, even if they're not like the correct gains, taking them, put them in your build, and see what happens. You're not going to hurt anything, and you may find something you really like. For example, As I discussed previously, the recommended gains for a fuzz face are 80 HFE for Q1 and 120 HFE for Q2. I know personally I prefer lower gain transistors because I don't really care about that maxed out fuzz sound of the fuzz face. What I care about is rolling down my guitar volume and hearing that overdrive sound. And in my experience, lower gain transistors clean up better, and I have better control over how much drive I get with the volume knob with lower gain transistors. So I prefer more like 50 and 70, or even putting two of the same, like 50-50, 60-60. That's just a personal preference that I found because I didn't listen to the people who told me to always use 80-120. So you can go and find out the gain and leakage of your transistors. You can obviously also find out if they are defective, like they're not amplifying at all, in which case, well, they're not going to work in your fuzz face, or any other pedal for that matter. But don't be afraid to buck the recommendations and try different stuff. That's the cool part about DIY is we get to experiment. We get to break the rules and build our own stuff and maybe find something really cool. And you never know, you may find something that will prompt you to design a whole new fuzz pedal that we haven't seen yet. So that's the exciting part that I hope you get out of this video, is the ability to follow the beaten path and then do your own thing. So don't get bogged down in numbers. They're just numbers. Try them in your pedals. That's what really matters. All right, so that's the end of the video. I hope you enjoyed that. I hope you learned something about germanium transistors. If you enjoyed the video, I'd appreciate you hitting the like button and subscribing, and hit the notification bell if you want to know when I make a new video. I'm Joe from Great Bench Electronics. Thank you for watching.